Tokyo Bay, before dawn. A barge floats in silence. No crowd, no fanfare, just steel. And a question nobody's answered. Can you build a bridge to space? Not a rocket, a structure, climbing straight up, past the clouds, past the jet streams, into orbit itself. It sounds impossible. Japan thinks otherwise. $100 billion committed. Decades of research behind it. A cable thinner than a finger, strong enough to hold the weight of a skyscraper. If it works, rockets become obsolete. If it fails, it could be the most expensive mistake in engineering history. Right now, no one knows which. This is the plan that could end the rocket age, or prove why it never should have started. The idea isn't new. Scientists floated it over a century ago. A tower reaching into orbit. Always dismissed. Always impossible. No material could hold its own weight that high. Steel snaps. Cables tear. Physics says no. Then came carbon nanotubes. Microscopic tubes of carbon.
As you can see,
Stronger
the carbon
than steel,
nanotubes are incredibly
lighter than
light compared
aluminium.
to the steel. The
Suddenly,
scale finally
the math started
stabilized
to
at
work.
0.0.
Japan took the idea seriously. A construction company, Obayashi, ran the numbers. A space elevator wasn't science fiction anymore. It was a $100 billion engineering problem. The concept sounds simple. Anchor a cable to the ground. Stretch it 96,000 kilometers into space. Attach the other end to a counterweight beyond geostationary orbit. Earth's rotation keeps the cable taut. Climbers ride up the line like an elevator. No fuel, no explosions, no rockets. Just steady mechanical ascent. But here's the catch. 96,000 kilometers is more than twice the distance to the moon. No material on Earth has ever been manufactured that long. Not even close. The strongest carbon nanotube cable ever built measures meters, not thousands of kilometers. Scaling it up isn't a small step. It's an unsolved problem in material science. And that's only the cable. The base station faces its own crisis. Something most people never consider. Weather doesn't stop for engineering ambition. Typhoons, lightning, wind shear at altitudes nobody has built through before. The ocean platform, meant to anchor humanity's first space elevator, might not survive its first storm season. Engineers had a plan for the weather problem. Build far from land, far from typhoon paths. The equatorial Pacific looked promising. Calmer skies, predictable winds, open ocean for kilometers. A floating platform, anchored by thrusters and cables. Always centered, always stable. In theory. In practice, the ocean doesn't stay still. Currents shift. Storms still form, even near the equator. And this platform isn't holding a ship. It's holding a cable stretching past the moon's orbit. Any sideways drift gets multiplied across thousands of kilometers. A 1 meter shift at the base becomes a catastrophic swing at the top. Engineers call it the whip effect. Move the bottom slightly, the top lashes violently. So they reinforced the platform, added dynamic positioning systems, GPS-corrected thrusters firing constantly. It worked in simulations. Then came a harder question. What about the cable itself, mid-air? At low altitude, jet streams rip through at over 200 kilometers per hour. A static cable in that wind isn't static for long. It vibrates. It oscillates. It could tear itself apart. Engineers proposed something radical. Let the cable move. Don't fight the wind. Bend with it. A flexible structure designed to sway without snapping. Brilliant on paper, untested at any scale resembling reality. Because nobody has ever built anything 96,000 kilometers long. Not a pipeline, not a cable.
The cable
nothing.
goes dark.
The longest
right at
undersea
this point.
cable on Earth barely reaches 39,000 kilometers. And that lies flat on a seabed. This cable would stand vertically, carrying its own weight, plus climbers, plus cargo, against gravity the entire way up. One engineer put it bluntly in an internal review. We are not extending technology. We are inventing technology that does not exist yet.
The cable problem needed a breakthrough. So researchers turned to carbon nanotubes again. Not just stronger material, longer material. In 2014, a Japanese team set a record. A carbon nanotube cable, just 3 centimeters long. 3 centimeters. The target was 96,000 kilometers. The gap wasn't small. It was almost incomprehensible. Scaling something a billion times longer isn't an upgrade. It's a different problem entirely. Defects multiply with length. One microscopic flaw, repeated across thousands of kilometers, becomes a fatal weak point. Manufacturing perfect nanotubes at that scale had never been attempted. Engineers needed a new approach. Instead of one continuous cable, they considered something else. A woven structure. Thousands of nanotube strands braided together. If one strand failed, others would carry the load. Redundancy instead of perfection. It solved one problem. It created another. Weaving material at that length required machinery that didn't exist. No factory on Earth was built for this. So Obayashi proposed something unprecedented. Manufacture the cable in space. Spool it out from orbit, downward toward Earth, instead of building upward from the ground. Gravity would help, not hinder. The counterweight in space would unwind cable as it moved outward. The far end would eventually touch the ocean platform below. It sounded elegant, until someone asked the obvious question. How do you align a single point in geostationary orbit with a moving platform 36,000 kilometers below? 1 degree of error at that distance equals hundreds of kilometers off target. Missing the platform wasn't a minor miscalculation. It was the entire project, drifting uselessly into open ocean. Engineers needed a way to guide the cable down with precision. The answer came from an unlikely source: GPS satellites, repurposed for real-time tracking. The descending cable end would carry sensors, constantly correcting its path as it fell toward the platform. Small thruster bursts, continuous adjustment. Like docking 2 spacecraft, except one end was 36,000 kilometers away. It could work, but it introduced a new vulnerability. Every sensor, every thruster, depended on uninterrupted power and signal. Lose contact for even a few minutes during descent, and the cable could drift off course permanently.
We have a
There would
signal
be
loss
no
on the main
second
deployment cable.
attempt.
It's
A
drifting. Trajectory is
96,000 kilometer
unstable.
cable
We need to
doesn't
abort.
get rebuilt easily. Then came the climbers themselves. Mechanical vehicles designed to ride the cable from ocean to orbit. No fuel. Electric motors gripping the cable with friction-driven wheels. Simple in concept, except climbing 96,000 kilometers takes time. Early estimates suggested over a week one way. A week exposed to solar radiation above the atmosphere. No shielding like a spacecraft would have. Human passengers faced a serious problem before the project even reached testing. Engineers shifted focus. Cargo first, people later, if ever. Even cargo climbers needed power for the entire ascent. Batteries alone couldn't last the journey. So they proposed laser-beamed energy transmitted from the ground, tracking the climber as it rose. A laser powerful enough to push a vehicle into orbit, aimed continuously at a moving target for days. Miss the alignment, even briefly, and the climber loses power mid-flight. Stranded between ocean and orbit, with nowhere to land and no way down. So, where does the project actually stand today? Obayashi's original timeline targeted construction by 2050. That target has already slipped. The cable problem alone remains unsolved. No one has manufactured carbon nanotube material anywhere near the required length. The laser-powered transmission exists only in small-scale tests. The floating platform concept has never been built at this scale. Every piece individually shows promise. Together, as one functioning system, it remains theoretical. Some engineers argue it's inevitable. Material science keeps advancing. Records keep breaking. What seemed impossible for towers a century ago became possible with new materials. The same logic might apply here eventually. Others are blunter. A space elevator may always stay just out of reach, always the next breakthrough away. Why does it matter, even unbuilt? Because the attempt itself pushes material science forward. Stronger, longer nanotube fibers have applications far beyond space travel. Aircraft, bridges, medical devices. The space elevator may never be built, but the search for it is already changing what materials can do. If it does succeed one day, the impact would be enormous. Launch costs could drop by over 90%. Access to orbit without a single rocket launch. A door into space left permanently open. Right now, it's still a plan. $100 billion of ambition waiting on a material that doesn't exist yet.
Whether it becomes the next great human achievement or remains an unfinished idea depends on a discovery nobody has made yet. If this kind of story interests you, there's more like it. Engineering attempts that push right up against the edge of what's possible.